Hi, this is the Displine team. Recently, our specialists visited China to carry out acceptance testing of robots for one of our clients. In this video, our Director of Innovation will explain what was done in China and what results were achieved.
Let's go through the checklist of what is required to perform the acceptance testing. The first item is a visual inspection for any physical damage, such as scratches or dents, as well as verification of all components and confirmation that all labels and markings are present. The second step is functional testing to confirm which of the customer's stated requirements are working as specified. For example, we test the water-resistant surface to ensure that the robot cannot be flooded. This test was carried out over a 24-hour period. We poured water and milk onto the robots under various conditions and evaluated their operational performance. Throughout this time, the robots continue to function without failure. We also need to test the laser safety strips used for detecting robots in the surrounding space. Next, we evaluate performance. This includes battery operating time and charging time, which must match the declared specifications, as well as the robot's ability to handle the specified load. In our case, this is 800 kilograms, and the test is performed using weight plates of the corresponding mass. After that, we assess speed, maneuverability, and software performance, followed by calibration. This includes verifying the software version and release, as well as proper calibration of sensors and navigation systems. These robots use SLAM navigation. There's a SLAM module, and QR codes are also placed on the floor. It is necessary to verify that the robots operate equally well using both SLAM and QR code navigation. The navigation test checks whether multiple robots can operate and move safely within the same area, using both multiple routes and a single shared route. The final test is a load stress test. In this case, the load refers to the robot's ability to lift a pallet from the floor, as we are working with pallet robots. The robot must extend its forks, lift the pallet, place it onto itself, transport it, and then lower the pallet back to the floor. It must perform all of these actions reliably. That covers everything we're going to test today. Now we will walk around all the robots and inspect them for scratches, chips, and various signs of wear. We will also press all the buttons and check that all bolts are properly tightened, nothing is squeaking, nothing is loose or jerking, the protective rubber parts are not torn, and that all components are functioning correctly. For example, these impact protection pads located on the forks, as well as this rubber strip, which also serves as a sensor. One of the key points in checking the external condition is shown here. For example, in this area we can see that the rollers slightly protrude beyond the base of the fork, while here they are flush with the surface or even slightly recessed. This is not acceptable. The manufacturer says this is normal, but it is not and must be adjusted. If a pallet moves onto the fork, it may catch on this roller. As a result, the effective fork height increases by the amount the roller protrudes. Ideally, all forks should be uniform. Uniform means correct. In this case, we are working with pallet robots designed to handle pallets, specifically wooden pallets, not plastic ones. Over there, you can see a typical standard wooden pallet with milk placed on it. We use this setup to verify that the robot does not leak and does not stop operating if it is exposed to spilled milk. Here is the robot. We exposed it to milk for more than 4 days. A pallet with milk containers was placed on it. The containers were punctured, allowing milk to continuously leak out. This is because we specifically ordered these robots modified to operate in conditions where liquid leaks are possible. And here is the charging station. It is currently in the process of charging. There is another design-related detail. To allow water to drain, special drainage holes were added. However, this display is positioned lower than the surrounding frame. As a result, you can see that the pin makes contact everywhere, and ideally this contour should be waterproof. We poured a significant amount of water and milk over it, and the display did not fail. Hopefully, this has been implemented properly. We are now testing the robot's ability to lift and lower a load that exceeds the originally specified limits. One of the key points is SLAM positioning. Right now, we're checking an error, a loss of SLAM positioning. This means we need to take the robot back to the location where its SLAM map begins. After that, it will be clear whether it loses SLAM or not. At the moment, it has just been switched from QR mode to SLAM positioning. These robots can have issues when handling pallets that are already shrink-wrapped. At this spot, the robot has a pad that prevents collisions. You can see it blinked, indicating a collision occurred. To allow the robot to automatically cut through the shrink wrap, the designers implemented special cutting knives. A human leg could get in the way, But these knives are designed to cut through the plastic without causing injury, because the fork motor cannot push the spikes deep enough to pierce a shoe or a foot. Let's see how this works in practice. Currently, we have 6 layers of polyethylene, actually slightly more because it's a bit crumpled. Let's observe how these forks pierce it. What we found during testing is that these polyethylene cutting devices are not strong enough to pierce the plastic. From a safety perspective, I tested them on my own foot. They do not pierce the foot and definitely won't pierce a shoe. Still, the device is unpleasant to touch, so using this pad with these forks is essentially useless. It's better to have the pad than rely on these forks. They're quite sharp and can cause injury if touched by hand. We found an alternative solution: pre-cut the polyethylene. It's better to do this while the pallet is supported on a piece of wood rather than hanging freely. If you make a cut here and a cut there, it creates a pocket through which the forks can easily pass. Additionally, in our case, the forklift usually places these pallets on the upper shelves, so there will already be some holes during receiving. By making cuts at the front and back during receiving, we can guarantee that the robot forks will not get stuck in the polyethylene, neither at the front nor the back.
Based on the tests conducted and our communication with the vendor, we can conclude that working with Chinese suppliers requires a particularly careful approach. All project details should be discussed in advance, and every stage of implementation must be monitored as thoroughly as possible. We hope you find this video useful. If you have any questions about robotization or the implementation of WES systems, our team is always ready to help. More information is available via the link in the description.